So the last topic we're going to talk about is convolutions, and these arise naturally from Laplace transforms. So let's say the Laplace transform of some function little f of t is big F of s, and the Laplace transform of some function little g of t is big G of s. No curly brace there. Then let's say these functions show up somewhere. So we get the function big F of s times big G of s, and we want to take the inverse Laplace transform. Is that at all related to little f and little g? Well, it is in this way. We call this the convolution of f and g. And convolution is defined with an integral. It's the integral from 0 to t of f of t minus u g of u du. That's the definition of convolution. So we'll talk in this video and the next video about some properties of convolution. Convolution is kind of an analog to multiplication. So some properties that you expect to be true for multiplication are true. For example, f convolved with g is equal to g convolved with f. And what that really gives you is another way to write this. We can just switch the roles of f and g here. So this is also the integral from 0 to t of f of u g of t minus u du. And you can actually show that these are equal. What this does is it helps you if one of f and g are more complicated than the other. You can choose either one of these to make your integral easier. And that's good. Some other things that are true, convolution distributes over addition. That basically comes from the fact that integration is linear. So we have this. We have that convolution is associative. Basically comes from the fact that you can switch the order of integration. And then we have that 0 convolved with f is equal to f convolved with 0 equals 0. We can see that if we multiply a function by 0, then the integral is still 0. Note, this one might lead you to believe that f convolved with 1 would give you f. But let's actually evaluate f convolved with 1, and we'll use this second definition of convolution for this. So we're going to take the integral from 0 to t, f of u, and then g is just going to be the function 1. G is always 1. So times 1, which is not multiplied by anything, du. This is not going to be little f of t, because we've got to integrate first and then sub in the bounds. So this is going to be the integral of f evaluated at t minus the integral of f evaluated at 0. That's not little f of t. For example, let's just do if f of t is cosine t. Right, then we're doing f convolved with 1 is going to be the integral from 0 to t of cosine u du. Integral of cosine is sine, and evaluated from 0 to t, so this is sine t minus sine 0 is 0. So f convolved with 1 here is sine t, which is certainly not cosine t. So this leads us to this question. Is there an identity, a multiplicative identity for convolution? Meaning, is there a thing I can put here instead of 1? And the answer is there is. It's actually the Dirac delta function. So all these weird things that we're throwing at you in the last couple weeks actually tie into each other. Let's just check that out. Let's look at f convolved with delta. Okay, now this is the integral from 0 to t. We're going to use that same second formula, so we'll put in delta for g. So this is f of u times delta of t minus u du. And now this is really close to the property. If I had delta u minus t, then that's the property where we pick out the value of f at t, right? But I'm actually going to make this claim. Delta of u minus t is going to be equal to delta of t minus u. Let's think about that. what is delta of u minus t? It's 0 everywhere except for when t equals u. And then it's infinite or something here. This is t equals u. 0 everywhere. And then delta of t minus u is the same. It's 0 everywhere except for when t equals u. And it's, air quote, infinite there. So what we're actually doing is we're reflecting the function about the line t equals u. And since it's symmetric about that line, they're equal. Okay, so I'm going to replace this. F of u delta of u minus t. And now I can use that property verbatim, where this means I'm picking out the value f of t. And I don't have to worry about u being between 0 and t because we're integrating from 0 to t. So of course u is between 0 and t. Okay, cool. So the delta function is the 1. If you take, if you think of convolution as multiplication, the delta function works like the 1 there.